Hello friends. From today we are to start a new course of mathematical physics, that is integral transforms of mathematical physics for BSc and MSc students. So this is my Insta ID. If you want to follow me on Insta, then you can follow me. Ozaloikazit123. This is my Insta ID. Okay. So what is the first topic that we're going to discuss here? So here, this is the first topic we're going to discuss, Fourier integral theorem. Right. So let's start. So before we start, please subscribe the channel, hit the thumbs up button, also share with your friends. So now let's discuss about Fourier integral theorem. So Fourier integral theorem, right? And suppose here you see, let me write the statement. It states that if a function f of x, right, satisfies the conditions given below, satisfies the following conditions. So what are the conditions? Let me write here. First, if it satisfies Dirichet's conditions. So what are the Dirichet's conditions? If you don't know, then just what's the first lecture of Fourier series, I'm going to provide you the link in the description box, because I'm not going to explain the conditions, Dirichet's conditions. Okay, so as I have already explained in Fourier series, if you haven't watched, then please go to the link, first lecture of Fourier series, given in the description box. Okay, then you're gonna better understand. Okay, so next condition is integration from minus infinity to plus infinity mod of f of x dx. Okay, this must be this converges. Okay, here you see, if the function satisfies these two conditions, then we can write f of x is equal to 1 by 2 pi integration from minus infinity to plus infinity, then again integration from minus infinity to plus infinity f of t cos u t minus x dt du. Or you can write the this result in this form as well, right? 1 by pi, if you change the upper limit and lower limit, lower limit, instead of minus infinity, if instead of minus infinity, if you write 0 here, so instead of minus infinity, if you write 0, then you're gonna have this result, right? So then we can write this. So meaning of the second condition is nothing but this function f of x is absolutely integrable in the interval minus infinity, okay, minus infinity to plus infinity, right, in this interval, right? So hope you have understood this. Now let's go to prove this theorem. Okay, so let's prove it. So we know the Fourier transformation, Fourier series of a function, and we have already learned that a function can be expressed in Fourier series if it satisfies the Dirichet's conditions, and that's why I request you to watch the first lecture of Fourier series. That's given in the description box. Link of that video is in the description box. So in this interval, the f of x in this interval, it can be expressed as a Fourier series. So that is given by this. Let me write here a naught by 2 plus summation from 1 to infinity an cos n pi x by c plus summation from n is equal to 1 to infinity bn sine n pi x by c. Okay, so here the value of a naught, an and b are respectively this. So let me write here, this is equation number 1. So let me give you the values of a naught. This is the value of a naught, how we can find a naught, and how we can find an is this is how we can find an. And let me tell you how to find bn is equal to this 1 by c integration minus c to plus c f of t sine n pi t by c dt. That's how we can obtain the coefficients a naught, an and bn, right? Now let us substitute substituting the values of the coefficient a naught and values of a naught, an and bn in equation number 1. What we're gonna have, we get this f of x is equal to, instead of a naught we have put this value, then we have got this down first, right? Then instead of an, let's put this value, right? Instead of an, let's put this value, right? So then what we're gonna have, we're gonna have this. Then instead of bn, so instead of this bn we can put this value, right? So then we're gonna get this result. So hope you have understood this, right? So now what we can do here, so what are the terms we can take common here? So we can simplify it as this. So 1 by 2 c integration from minus c to plus c f of t, this can be taken common, right? So after taking common this, what we have got, we have got this result, right? So let me write here. So that is into dt, right? That's what we have got. So here what we have done, we have taken this part common, right? From here also we can take this part common, and from here also we can take this part common, right? So after taking common we have got this. Now here you can see, you can compare this one with cos a, cos b, this is a, this is b, then sine a minus sine a, this is sine b, and that is equal to cos a minus b. If you apply that formula, if you apply that trigonometric identity, then it's gonna give you this, then we're gonna get this result, right? So this is the result we have got, right? Let it be equation number 2. Okay, so now let me copy equation number 2 and let me go to the next slide. Okay, so here is the equation number 2. Let me write the equation number 2 again here. This is equation number 2. Now cos function is an even function. Let me tell you how. Because you see, cos of minus theta is cos theta. Because you see, if you apply the ASTC rule, so here this quadrant is quadrant of cos. So here if you take minus theta, then this is the quadrant of cos. So cos minus theta, here it's gonna be cos theta, right? So this is even function. Even function means, what do you mean by even function? If f of minus x is equal to f of x, then f of x is said to be even function, right? Hope you know these things. So now you see, so if since this cosine function is even function, so that's why as cos minus theta is cos theta, so that's why we can write this part of this equation 1 plus 2, which is within curl bracket, right? This part of this equation we can write this way, right? We can write this way. So let me tell you why. Here you see, because as I have already told you that cos minus theta is cos theta, so therefore when you go from if you put n is equal to 1 here in this function, cos n pi by c t minus x, so if you put n is equal to 1, whatever will be the value of this function, the same value will be obtained on putting minus 1 as well, n equal to minus 1. Similarly, for n is equal to plus 2, what will be the value of this function for n is equal to plus 2, that will be equal to the value of the function, value of this same function for n is equal to minus 2 as well. So similarly, so what we're going to get here, you see, so if we put n is equal to 0, then cos we're gonna get the value of this function cos 0, that's gonna be 1, right? We're gonna get this 1, right? And this, as we have 2 here, so it can be written this way, that this can be written this way: summation of this function cos n pi c by t minus x from n is equal to 1 to infinity plus summation n is equal to 1 to infinity cos n pi by c t minus x. Now you see, as the value of this function at n is equal to plus 1 is same as at n is equal to minus 1, and the value of this function will be value of this function for n is equal to 2 is same as the value of this function for n is equal to minus 2. So that's why we can write this as, if we have expressed this summation from plus 1 to plus infinity, so we can express it from here you see minus infinity to minus 1, and combining these two we can express this way, right? Combining these two we can express the summation this way, from minus infinity to plus infinity, including this plus 1, right? Because at n is equal to 0, we're gonna get 1 of this function, value of this function, we're gonna get 1. So hope you have understood this. So including these two as well as plus 1, we're gonna get this, right? So hope you have understood this. So let me clean these things. So now just wait. Okay, so what I have written here, let me clean these things. Just wait, give me a second. So what you're gonna get here, you see, using this result in equation number 2, we get this, right? We're gonna get this result. So what we have done here, we have used this result in equation number 2, right? So that is what we have got, right? Now you see, it can be written this way. If you take here 1 by 2 pi, if you take 1 by 2 pi common, then or you can say that multiplying both numerator and denominator by pi, then we can write this one as this. This is equation number, suppose 3. Now here you see, if you multiply this sorry, not this one, if you multiply this one and this one, then again you're gonna get this, right? Because pi gonna be cancelled here, right? So hope you have understood this. So now why I have done this, so let me tell you. As we know that integration can be expressed as a sum, limit sum, right? So that's why you see what we can do here. Let me tell you here. So we have assumed this condition as well, as we are taking this function as as this function satisfies the Dirichlet's conditions. Dirichelt's conditions. So it must this is uniformly, it must satisfy this condition that f of x uniformly convergent, right, in the closed interval, that's minus c to plus c, right? So we can write n pi by c is equal to, suppose, u, and hence n pi by c as du, because you see integration of du, that can be written as u, which is an integration can be expressed as sum of this limit sum of du. Here we can take the sum of pi by c, because here you see this when I represent that n number of pi by c, then n pi by c, this is going to give you n pi by c. So if you consider du as pi by c, right? So hope you have understood this. So using the definition of integral as a limit sum of then we can write that limit c tends to infinity pi by c n is equal to minus infinity to plus infinity cos n pi c t minus x, and using these conditions, that using the definition of integral as limit sum, then we can write integration from minus infinity to plus infinity, then pi by c will be replaced by du, cos this part is replaced by u, right? Then t minus x, then this part is taken as del u, right? So hope you have understood this. And let me take this as equation number 4, and also this can be written this way, or this result also can be written this way. If you change the limit from minus infinity to plus infinity, if you change it to 0 to infinity, then 2 should be multiplied, right? Then 2 should be multiplied du. This is equation number 5, right? So if we use the equation number 4 in equation number 3, let me take you to the first slide, then you're gonna get this result. Here you see, then you're gonna get this result if you use equation number 4 in 3, right? Let me go to the last slide. Here you see, if you use this equation in 3, you're gonna get this result. Let me go to the first slide. Here you're gonna get this result, and if you use equation number 5 in 3, then you're gonna get this result. So let me go to that slide again. So if you use this in equation number 3, then you're gonna get the second part, this part, right? So now let me copy equation number 3. Let me copy the equation number 3, equation number 4, and equation number 5, and let me go to the new slide. Okay, so then what we're gonna have, so these are the 3 equations. This is the third one, equation number 3. So let me write this equation number 3. This is equation number 3. Right, and this is equation number 4, and this is equation number 5. This is equation number 5, right? So let us use equation number 4 in 3. Using equation number 4 in 3, if we use this equation number 4 in 3, right? So if you replace this part, right, taking c tends to infinity, then this minus c will be minus infinity, then this plus will be infinity, plus infinity, right? So that's why this equation number 3 becomes this. So we're gonna get this result. Yeah, here is the result, right? And if you use equation number 5, if you use this result in equation number 3, then what we're gonna get? We're gonna get this result. And putting 5 in 3, we're gonna get this result, right? So the Fourier integral theorem is proved, right? So these are the two results, okay, which are required. So in the next video we're gonna solve examples. So we're gonna discuss about the applications of this theorem. Using this theorem we're gonna solve problems, okay, in the next lecture. Okay, so see you in the next lecture. So stay connected. Thank you for watching.